today I want to introduce our recent works with the help of the neural network potential energy surface. Our research interests are only focused on two areas. So the first one is interaction between the metal ions and the biomolecules, as we know. So nearly 50% of our proteins use metal ions as a cofactor to achieve its function and maintain its structure. So the second one is the reaction network of complex systems, such as the reaction mechanism of enzyme and the gas phase complex gas phase reactions such as combustion. So here I have one example for the metalloproteins. So several years ago, we want to study the interaction between the zinc ion and one protein called MMP3, which is very important for the growth of the cancer. But when we simulate it with traditional force field, we found that for example, from the view of quantum chemistry, so the zinc ion should have 4 ligands and with tetrahedral coordination geometry. But after the simulation with classical force fields, so the coordination geometry is ruined. So it have 6 ligand and with this called octahedral geometry, which is wrong. This is the fault of the classical force field because it only uses electrostatic and van der Waals interaction to describe the interaction between the metal and its ligands. So by solving this problem, we developed a new force field called QPCT, which in this force field we add the charge transfer and the polarization. So compared with the classical force field, such as the amber force field 14 SB, the QPCT force field is more accurate, but it's not accurate enough because it cannot describe the formation and the breaking of the coordination bond. So after that, we are thinking whether we can directly use the ab initio MD simulation to simulate metalloproteins. But the protein is very large, so we cannot perform the ab initio MD simulation directly. So we employ the divide and conquer algorithm. So we cut the protein into small fragments and perform the quantum calculation for each fragment separately, and then combine the results, for example, the energy and the atomic force, and then perform the MD simulation. In principle, this method is accurate. It depends only on the quantum level we used, but its efficiency is far beyond. Is not satisfy our demanding, because even we cut the protein into small fragments, we still have to perform the quantum chemistry calculation. Another example is the simulation of the combustion reaction. As we know, the CFD simulation is a key step to design the for example, design the engine. So, but when we want to perform the CFD simulation, we need to know which reaction is a key reaction and the thermal chemistry parameters, for example, the rate of the reaction. But with only the experiment, we cannot know what happened in the combustion. So in the past almost 3 decades, so the theoretical methods is the main tools to study the combustion mechanism. And there are 2 main tools, theoretical tools. The first one is the transistor calculation. So one can imagine what reaction should be in the combustion first, and then calculate the transit state. And the other one is reactive MD simulation with, for example, the force field. However, the reactive force field is doesn't have straight physical meanings. So that means that its accuracy cannot be guaranteed. For example, in recent studies of Professor Curly-Han and Professor Heide-Golden, they both of them found that the accuracy of the reactive force field is not as high as we want. For example, to study simple system, the combustion of hydrogen, and the professor has gotten they select several reactions from the reaction network and calculate the reaction energy by using the CCSDT, the omega B79 functional, and several parameters of the reaction force field. And we can find that the error, it takes the CCSDT results as a reference. The error of this force field can be as large as 15 kcal/mol. So and when we have the equation to calculate the reaction rates, if the reaction energy, the error is as large as 15 kcal/mol, so the risk can be very unreasonable. So to solve this problem, we in several years ago we still employed the divide and conquer quantum calculations, because the gas phase reaction is mainly driven by the two-body collisions. So it's very suitable for the divide and conquer algorithm. But the same problem is that even we cut the whole system into very, very small fragments, we still have to perform the perform the quantum mechanical calculation. So the MD simulation with this method can only be performed within maybe 10 picoseconds, which is not enough to explore the real reactions in the combustion. So as covered by the previous talks, maybe the machine learning potential energy surface is the answer to balance the efficiency and the accuracy of the MD simulation. So I think the algorithm of the machine learning potential energy surface or the neural network based potential energy surface is already covered by the previous studies talks. So maybe I just skip this slides and focus on our applications. So our first applications is hydration of the zinc ions in water. So we employ the BP style neural network, and we trained the energy of individual water molecules and the energies of the interactions in the zinc binding group. The zinc binding group is defined as a zinc ion and the water molecules in its first and second coordination shell. And another thing is we also trained the charge distribution in the zinc binding group, because when the coordination bond is formed, so the ligand will donate electrons to the metal ion. So the charge of the metal ion cannot be, for example, for zinc, cannot be +2. So we calculate the charge distribution by quantum chemistry methods and train the neural network to learn this charge distribution. So by using this method, we simulate the hydration of the zinc ion. And here is the two results. The first one is the radial distribution function of the water around the zinc, as we can see. So the results, for example, the peak of the first and the second coordinate cell and the number of water molecules in the first and second coordinate cell all agree very well with the experimental measurements, especially when we include the charge distribution in the zinc binding group. And compared with the classical force fields and even AMD simulations, the results of the neural network potential is the best, because compared with the classical force fields, the neural network potential contains the key quantum effects such as polarization and charge transfer. And compared with the AMD simulation, the neural network potential can be we can perform longer MD simulations, so we can sample more configurations in the trajectory. And secondly, the efficiency of the neural network potential is much higher than the AMD simulations. We can label our data at higher level quantum chemistry level. And the second result is actually absorption near edge structure spectrum, and we can show that the results from the simulation of the neural network potential also agree well with the experiment. Another example is the combustion of methane. So by using the neural network potential, actually it's deep MD kit. So we perform the MD simulation, reactive MD simulation starts from 100 methane molecule and 200 oxygen molecules. And within, I think, within 5 days, we can finish the 1 nanosecond MD simulation, and the time step is 0.1 femtosecond. And from the trajectory, we detect 500 molecular species and almost 800 reactions, and 130 of these reactions can be found in the available database, such as the GREMAC. And from the trajectory, we can analyze every single reactions. So, for example, from the methane to some K intermediate molecules such as the formaldehyde, and then finally to the carbon dioxide. And this 32 main reactions are consistent with the experiment. So let's think about the way to train a new network-based potential energy surface. So I think the key is how to prepare a reference dataset, because there are already some available molecular descriptors, such covered talked by Professor Jiang in the morning, and the training process is I think kind of straightforward. And so the key is how to prepare the reference dataset, especially for the study of reactions, because we cannot know what kind of reactions will be happening in the MD simulation in advance. So when we prepare the reference dataset, we want our dataset can cover the target chemical space, and we want our dataset can be as small as possible, so we can save the computational cost of the quantum chemistry calculation, and we can label our data at higher quantum level. So to achieve this goal, we apply the active learning algorithm. So for example, when we prepare the reference dataset for the simulation of a combustion, we firstly use the ReaxFF to perform one simulation, and from the trajectory we collect some data, and we use the k-means method to remove the redundancy in this data and label it. And then with this data set as an initial data set, we perform several rounds of active learning to collect more of configurations with the potential energy surface given by the neural network. And here is an example. So by using, this active learning procedure is used for the simulation of the methane combustion. After that, we collaborate with Dr. Li Fengzang and Dr. Han Wang to use the DPG method to perform a simulation for the pyrolysis of the endodecan. And with the help of the DPG, we can use only 40,000 data and achieve the simulation of the launching alkanes and for maybe several nanoseconds, I think that. So this the pyrolysis of the endodecan is more complicated than the combustion of methane. But when we prepare the reference dataset for the combustion of methane, there are nearly I think 0.6 million structures in the dataset. But when we use the concurrent learning method, we can only collect maybe 40,000 structures in the reference dataset, which greatly reduce the computational cost. And by using the DPG, we also perform the reactive MD simulations for energetic materials. And we explained, why the core crystal of the Cl20 with TNT is more stable than the single crystal of the Cl20. And we also explained a very interesting energetic material which called TX. So in the reaction of the TX, it not the TX molecule not only decompose into small species, it can also polymer together to form larger molecules. So by comparing with the experiments, we explain the molecular mechanism behind these reactions. And another example is the formation of shoot. So as we know, the shoot is formed in the incomplete combustion process, and the shoot molecule is actually is the second largest supplier of the greenhouse effect after the carbon dioxide, and is also harmful to our health. But the molecular mechanism behind the formation of the shoot is unclear. For example, we know some radicals will be formed in the incomplete combustion, and then it will be gathered to form some polycyclic aromatic carbons, we also called pHs. But the atomic detail is unknown, and more importantly, how the gas phase pH can form the solid phase, the shoot particles is even more complicated. So we set up several reactive MD simulations with neural network potential energy surfaces. So the reactants is acid and 5 typical radicals from the incomplete combustions. And start from this reactants, we observed the formation, for example, the formation of the 1 ring pHs and the formation of the 2 ring pHs in the trajectory. And for example, these two paths, path 1 and path 4, already be proved in the previous studies by using theoretical calculations or experiments. But the path 2 to path 2, path 3, and path 5 are all new reactions we found in a single trajectory. Indeed, we can perform a lot of trajectories, but in a single trajectory, we can already found some new reactions. And there are also some larger pHs, and some of them already be proved in some of the reaction paths already be proved in previous transition state calculations, but some of them are new paths found in our simulation, and the products are consistent with the experiment. And if we keep simulate the reaction, we will find a larger pH and new reaction mechanisms. So the largest pH we found in the trajectory contains about 9 to 10 rings. And one interesting phenomena is that even we perform hundreds of MD simulations, the largest pH we can find is contains no more than 10 rings. That's because to form the larger pHs, the main mechanism is the radical chain reactions, because in the pHs, the electron can be delocalized, in the whole molecule. So the larger the molecule is, so the stable the radical is. So if the pH radical is small, so it can combine with another small radical to form a larger one. But if the pH radical is already very large, so it's already very stable, so it will not react with other small molecules to form a larger one. So here we can explain the growth mechanism of pH, but we cannot explain the formation of shoot particles. But indeed, from our trajectory we found some shoot inceptions. Because it's said we cannot call it shoot particles, but it can be the shoot inceptions. And we found that these shoot inception will not cannot be found from the large pH. Instead, they are mainly formed from these small pHs. Several experimental works gave the similar conclusion, but we still working on this and try to combine the simulation and the quantum chemistry calculation to prove that this mechanism is correct. So when we simulate the chemical reactions, as I told, the main difficult is obstacle is to prepare a reference data set, and normally we employ the MD simulation to sample the data, but when we perform the simulation on the maybe lower temperatures, we found that it's very hard to sample the data, around the barrier area of the potential energy surface. To solve this problem, we recently employ the enhanced self-organizing incremental neural network. Actually, the algorithm behind this measure is kind of simple. For example, we have a lot of data. So the blue cross is the raw data, and the ESOIN measured, we can learn the topology of these data and use some node, for example, this red circle, to represent the raw data, and each node in the neural network can contain two important features. So the first one is the structure of the data, and for example, the structure of the molecule, and the second one is the density of the data. So for example, if this is our raw data, and after the training of the ESIN, we can use this nodes to represent this raw data. So each node can represent the density of the raw data and the relationship of the raw data, and more importantly, it can give us the age of the raw data, so we can know which part of the potential energy surface we haven't explored. So here is the algorithm of this measure. Maybe I can skip it. So the key idea is that when we add one new data into the ESOIN, we don't have to retrain the whole neural network. It can be trained in an incremental manner. And in this measure, every time we put a new data here, we will determine whether we should add a new node to represent this data. And by round by round of the training, so we can finally got the topology of our data. And if we have the age of the subset of our data, we can use some enhanced sampling method. For example, we can use the metadynamics to start from this node, and the aim is this node to perform the MD simulation. So which can exploit this part of the potential energy surface. So this is the framework of this measure. So in the beginning, we should have some initial data set, and then with the help of the ESOIN, we can exploit the target chemical space gradually, and then we can pass the data to a neural network model, and we add a error indicator, which is very simple. It's the prediction error of the atomic force to indicate the predict power of the neural network potential. Here is
sorry, we need to wrap up in 1 minute or so. Yeah.
Okay, yeah, I can finish that. Okay, so there's two examples. The first one is we want to train neural network potential to predict the potential energy surface and atomic force for water clusters contain 1 to 9 waters. So as we can see, in 6 round of training, we explore the chemical space gradually, and maybe I skip this. So here I want to demonstrate that the final model, the accuracy of the final model is good enough, and we can also detect some typical stable water clusters in the MD simulation. And here is another example for the the potential energy surface of the tree peptide, and for the metalloproteins. Okay, So we also design a web-based interface for this method. So if you want to use this software, you can download it from our GitHub. Okay. Okay. So all of these calculations are performed by my 4 students, and I would like to thank a lot of my collaborators for their help. Okay. Thank you very much.
Thank you. So we have maybe some time for 1 or 2 quick questions. Any questions from the audience, please?